What's up, everyone? Welcome. Thank you for all waking up so bright and early. So I'm Ben. I'm going to be introducing some of the lovely speakers this morning. Before we do that, I know that Pandya has put an incredible amount of work and time and energy into this project, so I think we should give her another round of applause, seriously. Thank you. In any case, our first speaker probably needs no introduction in this room. But he's going to be talking about the future of ETH 2.0 and some research. So let's please welcome to the stage Vitalik Buterin.
Okay, hello everyone. Hope you've had a good morning. Raise your hands if you have a good morning. Raise your hands if you haven't. This side of the question always gets no answers for some reason. It's strange. So today I'm going to talk about one of the technical developments that's not going to become relevant to Ethereum 2.0 immediately. It's a slightly later stage thing, so possibly phase 2 shortly after phase 2. I've been calling it part of phase 3, which is the introduction of a CBC Casper into the Ethereum 2.0 proof-of-stake blockchain. So first thing, I should start off by introducing what CBC Casper is, right? So CBC consensus is this a new school of safe under asynchrony Byzantine fault-tolerant consensus, meaning the kind that works, originally invented by Bls Aggregation. And the main theme of CBC Casper is that you have basically a proof-of-stake chain, so you have validators, and validators keep on making blocks, and when they make blocks, they make a block on top of the chain that they consider to be the best chain. And they might pick this with what Vlad calls an estimator, I call a fork choice rule, and fork choice rules are pretty common. So for example, the longest chain rule in Bitcoin or in Ethereum is a fork choice rule, except here there's a twist, which is that unlike the longest chain rule, where no matter given any particular chain, there's always the possibility some longer chain exists. Here there exists this possibility of a kind of a lock-in mechanism, where once enough validators build on a particular chain for enough rounds, then according to the rules of this fork choice rule, it's that chain becomes locked in. It's like not possible to switch to voting or building on another chain without a huge portion of validators like basically committing provable violations, which means they get their deposits slashed. So in CBC Casper, finality, the concept of when you know that a block is not going to be reverted is client-side. So what this means is that you don't need to choose hard thresholds in protocol. Like the number 2/3 that you might see in BFT protocols more commonly does not appear in CBC, right? Like you can choose for yourself a threshold of 2/3, but you can choose for yourself a threshold of 0.8 or 0.55. And every user personally has the ability to kind of choose for themselves their own trade-off between aliveness and safety. So Lmg Ghost, it's this fairly important building block of at least the version of CBC Casper that I'm going to be presenting here, right? So what is Lmg Ghost? So it stands for latest message-driven, greedy, heaviest observed subtree. So it's an adaptation of the Ghost protocol created by Jonathan Sombolinsky and Aviv Zohar back in 2013 to a proof-of-stake context. And the way the Ghost protocol for proof of work worked is basically that instead of looking at the longest chain, you do this kind of block-by-block procedure where every time you reach a block that has 2 children, you pick the child that has more blocks in total supporting it, even if those blocks are not part of the same chain. Now, in latest message-driven Ghost, which is this adaptation to proof of stake, we don't look at all of the blocks that have been made because, like, unlike in proof of work, where making 10 times more blocks requires 10 times more computing effort, in proof of stake, you can sign as much as you want, so there's not much more points in counting. And so we look only at the most recent messages of any node as evidence of the most recent opinion of what that particular validator is favoring, right? So now, if we can look at this through a diagram, so let's assume a kind of simple model where the only thing that happens is blocks. You don't have attestations. You don't have you don't have any more complicated messages. You just have blocks. So you might imagine time being kind of split up into epochs. During each epoch, every validator has a chance to create a block. So here we're assuming 5 validators, where each validator makes a block once over here on the left. So A, B, C, D, and E are the validators, and then each validator makes a block on the right. And so if from your point of view as a client, your view, so the blocks that you have seen, end with this, then you figure out what the latest blocks are created by each validator. In this case, from A, it's going to be this one. From B, it's going to be this one. From C, it'll be this one. From E, it'll be this one. And from D, it's still this one because we haven't heard a block from D in this epoch, right? So this is what latest message driven means, right? So now, what does ghost mean? So the idea is that we're going to focus on these 5 latest messages, and we're going to assign a score to each block, where the score of the block basically is the total number of latest messages that are supporting that block. So this block only has one block supporting it, which is that block itself. This block only has a score of 1. This block has a score of 1. This block is supported by itself and by this block, so it has a score of 2. This block has a score of 4 because it's supported by this, 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 and this. Now it's not 5 because this block itself is not a latest block, and so it doesn't count. This is also 4. Now here we have 1, and then this finally goes up to 5. Now, you might notice that scores go higher the older a block is. So we're not going to just pick the block with the highest score, right? The idea here is that we're going to start with the genesis block, so start over here, and then if there's one child, we hop over to the child, and then if you have a choice between 2 or more blocks, then you pick the side that has a higher score. So over here you pick bottom, then you go to the right, and then over here you pick middle, because middle has a score of 2, and then you go forward, and this ends up being your head. Now, you might ask, well, why do we care about using Lmg Ghost, right? So for example, just a simple longest chain rule would also pick this block in this particular case as the winner, because this block is the unique block that has a chain of length 6, and so even on the longest chain rule, it wins as well. So why not just use the longest chain rule if it is simpler? So the reason why we use Lmg Ghost is that there's 2 parts to it. One of them is a kind of common property of Ghost in general, which basically is that longest chain rules cannot take into account information from frequent parallel attestations. So what does this mean, right? So what this means is that in the current Ethereum chain, you have a block coming once every 14 seconds. And so on average, something like over 91% of all blocks make it as part of the main chain. And so we can kind of not care about what those blocks that are not part of the main chain say because they don't really affect things that much. But now imagine we wanted to have a chain that comes to consensus faster. And so instead of 1 block every 14 seconds, we had 14 blocks every 1 second. Now, if you do something like that, then almost all of those blocks are not going to end up being part of the same chain, right? Just because of network latency. If I publish a block, by the time that block reaches the entire network, there will be 100 other blocks that other people will have published. And so the kind of depth of the chain, the length of the longest part of it, will be maybe 1% of the total number of blocks. So the problem with this is that if you have an attacker, then an attacker just running on their own server could more easily just create a chain which is much longer because they can perfectly coordinate with themselves. They don't have any network latency. So, but in reality though, even if you have an attacker that can make longer chains, like there's plenty of information that says that the chain the rest of the network is working on has more support, right? You can just look at it and you can see that there's like 100 times more people building on the real chain than there are people building on the attack chain. And so the question is, well, how do we have a kind of formally defined fork choice rule that actually takes this information into account? And Lmg Ghost is the answer, right? If two blocks appear in parallel, they still both count as support for whatever their common ancestor is. Another interesting property of Lmg Ghost, and this is very important to CBC finality specifically, and specifically important to Ghost in a proof of stake context, is that the minority can never beat the majority regardless of how many messages the minority sends. So in this particular case here, right, we have 5 validators, once again, and you might notice that 4 of them are kind of peacefully, happily coordinating on building up one chain. I mean, you see C and D make a little bit of a mistake, but otherwise it's just going on fine. And then you have B off in a corner, possibly disconnected from the network, possibly trying to attack it. Now, imagine B makes 500 blocks. If you use the longest chain rule, B would win. If you use proof of work style Ghost, B would also win. If you use Lmg Ghost, B would lose because all of those blocks come from B, and we only count the latest message anyway, so when you make a new message, it overwrites everything that you said before. So from these 2 properties, what we get is a fork choice rule, which is both kind of very friendly to ETH 2.0's goal of trying to coordinate on blocks very quickly, and at the same time, something that looks like it might actually kind of finalize in the same sense something like Casper FFG finalizes. So let's take a look at this view that I showed you in this slide more closely, right? So let's assume the thing at the top is your global view. So you are happily running an Ethereum node, and your happy Ethereum node has received these blocks from the network. So that's your global view. From your global view, you can infer things about the local views of each of the validators. So for example, one thing you might notice here is that A made their most recent block over here. And so if A made the most recent block over here, that means that at that recent point in time, A was aware of these 4 blocks, and at that particular point in time, A considered these 4 blocks to be the latest messages. If you look at C's view, C built a block over here, which means C was aware of these 4, which means you know that C sees that these 4 latest messages are kind of pushing the fork choice rule in this direction. You know the same thing about D's view, and you know the same thing about E's view, right? So each of the 4 validators, except for B, sees the chain and sees that everyone else is also building on the same chain. So from this information, we can make a claim, right? And the claim basically is that unless at least 2 validators make blocks that violate the protocol rules, so make blocks where you can just take that block, put it together with a block the validator made before, and you get a proof that the validator violated the protocol, then the chain will, basically, unless at least two validators break the rules, no validator except B has the ability to make a block on top of the top chain. And so the only thing that can keep growing is the bottom chain. And so we say the bottom chain, or specifically A, is finalized with a, quote, safety margin of 2, right? So how do we justify this? Well, first of all, it's a rule of CBC Casper that for a block to be valid, that block must be the block's parent must be the result of executing the fork choice rule given all of the messages that that chain knows about. And so here, well, can A build a block over here, right? So first of all, for A to do this, then A would build a block over here, but then no one else had built a block yet. And so, well, A would be clearly violating the rules because A moved from a chain that has more support to a chain that has less support. Can C legally move to the top chain? Well, no, because C built a block on this chain that's supported by 4 validators, and this chain has 1 validator, so C can't legally move over. Can D legally move over? No. Can E legally move over? No. And it turns out that you need any two of these validators to break the rules and illegally move over to the top chain for everyone else to be able to follow and for the top chain to win. So this is why A is finalized with a safety margin of 2. Now, you might notice here that this concept of safety is completely subjective, right? All that we have here is validators following a fork choice rule. We just have validators following a version of Ghost that's been adapted to proof of stake, and that's been adapted to this context of a kind of bounded validator set. And out of this, you have this concept of finality. Even though you do not have an explicit 2/3 threshold, you do not have an explicit concept of preparing and committing, you don't have any of these kind of explicit ideas that exist in either Casper FFG or more traditional Byzantine fault-tolerant consensus algorithms more generally. Right, so this seems like what we've basically managed to do is we've managed to build this concept of finality, which previously was a more kind of the domain of these BFT algorithms, on top of a proof of stake algorithm that looks very chain-based. So it looks very similar to just some of the older proof of stake algorithms that people have been doing for the last 5 years, except by switching from longest chain to LMG Ghost, you just kind of unlock the ability to get this finality property. Right, so basically what this says is that A is finalized unless unless 40% of the validator set is willing to burn all of their money to cause the consensus to shift over. So more generally, in the context of LMG Ghost, there exists a heuristic called the 2-round clique oracle, which says if there exists a 1/2 plus P sized subset of validators that all support the same chain with 2 consecutive messages, so 2 rounds of messaging from 1/2 plus P, then the earliest of the blocks signed in those 2 rounds is finalized with safety margin P. Now, if you want to solve for kind of maximizing safety and maximizing liveness, then you might want to set P to be 1/4. And so if 3/4 of the validators support the same chain with 2 rounds, then you get a safety margin of 1/4. So the 2-round clique oracle is sufficient, but it's not necessary for finality. So there's also the 3-round clique oracle, there's the n-round clique oracle, there's potentially other kinds of oracles. So there's this extremely large space of heuristics that you could potentially use to kind of compute whether or not finality is happening locally. So cool things about CBC Casper, right? So why is this potentially interesting? So first of all, different clients can privately choose different required safety margins at which they show a block is finalized. And especially if a client believes that some subset of nodes are permanently offline, it can privately use that information to verify finality. So for example, let's suppose that 72% of Ethereum staking is done in Antarctica. And let's suppose Antarctica suddenly gets blown up by a nuclear war. Oh no, 72% offline. What am I gonna do? So in a traditional BFT context, right, you just don't finalize anything. You lose any notion of finality at all. But here, if I, as a validator, privately know that Antarctica has been blown up and 72% of the proof of stake validators are gone, then I can use that information and incorporate it into the fork choice or into the finality gadget. So I can say, oh, I am going to reduce my threshold from 2/3 to 2/3 times 28%. And then to me privately, the chain is going to keep giving me guarantees of safety that are conditional on my own information. You could potentially do even more advanced things. So you could potentially have an opinion that some particular subset of validators is more trustworthy in some way. And so you could just privately assign them more weight. So there's this extremely large space of things that individual clients can just personally do. And the responsibility of figuring out what level of safety guarantees they have is sort of offloaded to the edges. Now, there are simple heuristics you can use, like for example, the 1/2 plus P 2-round clique oracle. But if you have more information, then you can use it. So you get, another benefit is that you get some amount of safety with just any amount online over 1/2, right? So if only half of Antarctica gets blown up, and 36% of validators go offline, in Casper FFG and in Tendermint and in these BFT algorithms, then basically they're either going to halt or they're going to stop finalizing, and you lose any guarantee. In Casper CBC, you still get potential, depending on what your oracles are, somewhere between 8 to 16% safety margins. So you still get kind of as much safety margin as you can get under more extreme circumstances. Another benefit is that this can be kind of bolted onto existing chain-based proof-of-stake blockchains very cleanly, right? So even just existing chains, if take NXT, Peercoin, like any of these, if they are willing to switch to Lmg Ghost, then which actually is not that much of a switch, because under quote normal conditions, like Lmg Ghost tends to just agree with whatever the fortuitous rule before was saying, then they could just have nodes privately run these safety oracles, give this extra safety guarantee, add these slashing conditions, and you have a Casper CBC system. It's extremely flexible. There's lots of different ways to kind of implement it and bolt it on top of other things. So why upgrade to CBC? Why isn't Casper FFG good enough, right? So honestly, FFG is kind of ugly, and the reason why is because it kind of glues together the FFG fork choice rule, which basically says highest justified epoch wins, with some underlying fork choice rule. So in the original Casper FFG paper, it would be gluing together the FFG fork choice with proof of work. In the current Ethereum Beacon chain implementation, it's gluing together FFG fork choice with Lmg Ghost. And this kind of ugliness has practical consequences. There's kind of bounce back and forth attacks between two chains, and there are ways to fix these attacks, but they're definitely less clean than what you've just seen from a CBC Casper, right? So that's one of the kind of bigger reasons, just increasing kind of conceptual simplicity and just decreasing the conceptual attack surface of the design, but also all of these other benefits of CBC that I talked about. So why is the Ethereum 2.0 phase 0 not using CBC, right? Why is it still using FFG? So one of the big reasons why we were not able to do this earlier was efficiency. So basically, the problem with implementing CBC is that you have these two conditions that you need to enforce. One of them is this validity condition I mentioned, which is for a block to be valid under the Casper CBC rules, the block needs to be the building on top of what the chain itself kind of thinks is the head of the chain, like in some sense, right? So the block itself needs to contain evidence that shows that the person creating the block has the right to build that particular block at that time on top of that particular parent. And this requires like basically executing the Lmg Ghost fork choice rule in protocol as part of the validity condition of a block. So in English, this basically says in order for a block B to be valid, it must be the case that given all the evidence included in B or its predecessors, B is the correct block to build. Slashing condition. This is the only CBC slashing condition. We're down to one. If a validator creates two messages, M1 and M2, where M1 does not reference M2 and M2 does not reference M1, then the validator's deposit can be slashed. So every message that you make has to reference the previous message that you made, and the chain that you're building on has to like basically include a superset of all of that information. So everything you say must reference the previous thing you said, forming a single personal kind of message chain. So the implication is that if you make a block that took into account some piece of evidence, all future blocks must also take into account that evidence. The problem is, of course, we have a beacon chain, we have a huge number of validators that are making messages very quickly. We make this practical in a Casper FFG context with kind of separating out blocks and attestations. So we have one block every 6 seconds, potentially thousands of attestations every 6 seconds. And we use this cryptographic technique called Bls aggregation that allows us to combine together a huge amount of signatures into one signature that in terms of data complexity requires 1 bit per participant, and in terms of one computational complexity requires 1 EC add, which is maybe 1 or a few microseconds per validator. The problem is that Bls aggregation requires many validators to be signing the same message, but CBC Casper kind of goes against that, right? So CBC Casper says every validator's message must reference that validator's previous message. And so it sounds like we're requiring validators to be each signing different things, which sounds like it might make Bls aggregation efficiently impossible. So here's a solution. Every block maintains a Merkle tree of every validator's most recent message. And so the way that you make sure that each validator builds on their previous message is that each validator builds on a Merkle root, which is the same Merkle root for everyone, containing everyone's previous messages. So a slashing condition basically says if a validator signs a message at slot C of a block where their most recent message was at some slot A before C, and they signed another message at slot B that's between A and C, then they get penalized. So challenges, right? Computing LMG Ghost takes a huge amount of time. There's this other version of Ghost called bitwise LMG Ghost, where instead of going block by block, you kind of make it even more finer grains and you go bit by bit in block hashes. And it turns out that this has a relatively efficient algorithm where you can store information inside of the chain about whether or not, basically the chain is valid. So for every validator, you can basically there's this algorithm that you can use, and you can basically get verification of LMG Ghost in something close to kind of k times some logarithmic time if there are k validators that are being changed per slot. So this is actually not much more expensive than what's happening already, where you have that many changes already happening to a Merkle tree. So these things are definitely possible. Now, what does this mean, right? So first of all, Casper CBC can just be bolted onto existing systems, including any form of proof of stake. But also, this means that Casper CBC has this path toward kind of potential faster deployment in Ethereum in a way that actually changes surprisingly little of how Ethereum itself kind of fundamentally works today, right? So CBC is definitely not something that's happening in phase 0 or phase 1, but it's also, there's no need for CBC Casper to be kind of Ethereum 3.0 territory. It's something that we can start getting the benefits of more quickly. Thank you.